Okay, so let's talk about functions and their graphs. First, let's get a couple of definitions down before we even get into graphing. So, first definition I want to look at is this thing called a relation. Now, we have a bunch of equations, okay? And sometimes we plug numbers in for one variable, see what comes out for another variable, all that great stuff. Well, a relation is a correspondence between data points. A relation has some kind of relationship. So sometimes when they're conducting experiments, they're like, okay, what happens if we do this? What is the result? What is the output? That would be a correspondence between data points. Whatever they put in determines the result, determines the outcome. Now, a function. Now, some of you may have learned the definition of a function by using variables. So I'm going to switch that up on you because we don't always use those same variables. And if you're like, which variables are you talking about? Good, I'm glad you don't know. And those of you who do know what I'm talking about, I need you to switch your thinking a little bit. So if a relation is supposed to be considered a function, if a relation is supposed to get a promotion to a function, because that's really what's happening here, then here's the deal. Every input gives me one output. Okay? So for every input, for every one thing that's inputted, you only get one result, one outcome. Okay? That's how a relation gets promoted to a function. Sometimes when experiments are conducted, they get two results out of the same input, out of the same thing that they did. But if something is considered a function, then for every input, there is exactly one output. Okay? That's all you get. Now, a couple other definitions, domain and range. The definition of a domain. The definition of a domain is the input. Sometimes the domain is also considered the independent variable. Now, the range, okay? The range is the opposite of the domain. So if the domain is the input, the range is the output. And also, the range would be considered the dependent variable. Because the output depends on what you input. Again, the output depends on what you input. Cool? Okay, so here are some basic definitions of functions. Okay, of a relation first, a function second, and then domain and range. So hang in there. We're going to look at some things and decide if these are functions or not. We're going to take a look at some mapping, some graphs, some data points. So hang. Okay, so let's talk about some applications of functions. In this particular case, they give me a mapping, and they're asking me to state the domain and the range for the following relation. Remember what I mentioned about a relation. A relation is a correspondence between data points. Okay? And they would like us to determine if it's a function. So you know what? Let's determine if it's a function first. So remember the definition of a function, right? My very quick definition. Every input goes to one output. So let's take a look at each input. If this particular mapping, notice the arrows start here at the left and they move to the right. That means the first name would be considered the input. And the last name would be considered the output because that's where it's ending up. Okay, so the first name is John. And the question is, how many outputs does it go to? Good, just one output. So is it a function so far? Yes, it is. What's your second input? Katie, good. And how many outputs does that Katie go to? Just one, still a function. The third input is Kia. How many outputs does Kia go to? Just one, still a function. Marcia, how many outputs does Marcia go to? Just one, so it's still a function. And last but not least, Jan. Jan goes to how many outputs? Just one. So is this a function? Yes, this represents a function. Every input went to exactly one output, and that's all that mattered. Every input went to exactly one output. Now, let's talk about the domain, and let's talk about the range. All right? The domain is the input, correct? Okay, so we're going to write it in set notation. So remember, we write the braces for set, and my input consists of John, Katie, Kia, Marcia, and then Jan. So this would be considered my domain. Now my range. My range is the output. So again, we're going to write it in set notation. And so our range is, or are the words Doe, Smith, Hill, and Brady, all separated by commas. Cool? Okay, let's look at another one. They give us another mapping, and the question is the same. They would like to know if this represents a function. And yes, they want the domain and range also. But let's determine if it's a function or not first, because that seems to be the easiest thing to do. So remember, every input goes to one output. So the input is being referred to as, good, the body parts are the input. Why? Because my arrow starts here and goes to the right. So that means the clothing items are the output. Okay, so the first input is feet. How many outputs does it go to? Just one. Is it a function? Yes. Let's look at the next input. It's head. How many outputs does it go to? Looks like it goes to two, because I see there's an arrow from head to hat, but also to earmuffs. That's two outputs for this single input. Is this a function? Nope, not a function. Okay, now let's look at domain and let's look at range. And by the way, I really don't care to check any further on my inputs to see if they go to one output. If it fails at one point, so to speak, it just fails. I don't really care about checking the rest of them. Okay, so the domain refers to the input, correct? And the input are the body parts, yes? But you have to list them, and you're writing them in set notation. So we have feet, we have head, we have legs, and we have torso. Good. And our range refers to the output. Excellent. And again, you need to list it. You just can't say clothing items. You have to list it. So we have shoes, hat, earmuffs, skirt, and then shirt. Good? Awesome. All right, let's take a look at another one. Now, in this particular case, they give me a set of data points, and they're asking me if these data points represent a function. They also want to know the domain and the range. Well, let's talk about the function first. Now, for some people, they can just look at it like this and go, oh, yeah, I can see if it's a function or not. And other people are like, yeah, I can't see it that well. So here's my recommendation to you. I recommend you create the mapping. I suggest you create this mapping. So I have an input and I have an output. We usually place the inputs on the left and the outputs on the right. So since these are points, they consist of an X and a Y, don't they? Well, my inputs will be X's and my Y's will be the outputs. So I'm just going to go down the list on my X's. I have 4, I have -9,
I have 6. And then I have 4 again. Well, I can't write 4 again because 4 only appears once on the number line, so I never write any duplicates. Okay, let's look at the outputs. We have 6. I have another 6. I'm not going to write it. No duplicates allowed because all these numbers appear only one time on the number line. Okay, so now let's create the mapping. So that first input, which is x, is a 4, and it's mapped to 6. My second input is -9, and it's mapped to 6. My third input is 6, and it's mapped to 10. And my last input is 4, and it's mapped to 14. Okay. So the question is, does every input go to exactly one output? Yeah, I think some of you said it. No, it doesn't. It fails here at the 4, doesn't it? 4 goes to 6, but it also goes to 14. So this is not a function. Now, let's look at the domain and let's look at the range. Now, when they're asking for the domain, they want it in set notation. See the little braces here? So the domain would be the numbers 4, and you have it listed, don't you? -9 and 6. And sometimes they would like these numbers in numerical order, so just watch their directions. Here they didn't really say, so I'm not going to be too concerned. And the range is the outputs, yes? Okay, well I have the outputs. They're right here. Those are the y's. So we have 6, 10, and 14. Cool? Loving it. All right, let's check out another one. All right, they want to know the domain and range for this relation, and then they would like to know if it's a function. So me personally, I always like to identify it's a function or not, and I like to create my little mapping. Why? Because I'm a visual person, and sometimes I just really need to see this drawn out. So again, these are points made up of x's and y's. So my x's are my inputs, my y's are my outputs. So let's see my inputs. I have -5, -4, -3, and -2. And my that's interesting. My output appears to be just a single number 5. Okay. And it looks like every single one of these inputs is matched to that single output. So the question is, would this be considered a function? Remember the definition of a function. Don't let the drawing fool you. Does every input go to a single output? Yes, it does. So yes, this is a function because every single one of these inputs went to a single output. And that's the definition, and that's all I care about. Now, let's look at the domain. Again, we're going to write it in set notation, and we have the domain already listed, don't we? Because of the mapping we created, so it's very easy to see. And the range, same thing, we're going to write it in set notation, and I only have a single number in the range. So be it. Cool? Be careful of this problem. This one likes to try to trick you. All right. And now they're giving me an equation. And their question to us is, does this equation represent a function? Agreed? So, remember the definition. For every input, you have a single output. For every input, you have a single output. So some people actually like to create a table. They like to plug in numbers for x and see what comes out for y. So what happens if we plug in 0? Because that's a nice easy number. 0 for x. How many answers do you get? Correct, you get just one, and that one answer is -8. Let's plug in another number. Oh, let's plug in 1. 1's a nice easy number. And when I plug in 1, what do you get? Yeah, you get 0. But the point is you get one output. You with me? Okay, let's plug in -1. Let's see what happens with the negative end of the world. What do we get when we plug in -1? I'm hearing you. -10. Good. I get a single output, though. That's the point. Agreed? So the question is this. Every time I now plug in a number for x, will I get just one number for y? Yes, in this case, you definitely will. So is this a function? Yes, it is. This equation is considered a function. And now that it's considered a function, we get to promote it. So when we promote it, the y is going to be rewritten. And we're going to write this y as f of x. That's how you pronounce this, f of x. And let me explain to you what this means. F is actually the name of the function. I could have called this name, okay, G. I could have called it H. I could have called it K. I could have called it whatever I wanted to. But most of the time we call it F. And why do you think we call it F? Yeah, because F stands for function. Now, inside the parentheses, please understand this is not a multiplication problem. Even though I said the word of, it is not a multiplication problem. This tells me what variable I'm going to find on the other side of the equal to sign. So since this says x, I'm going to find x's on the other side of the equal to sign. Are you with me? So I do see x's there, don't I? But you know what? Maybe instead of this saying f of x, maybe it said f of t, which means what would I have found on the other side of the equal to sign? Yeah, I would have found a bunch of t's. I would have found 3 times t squared plus 5 times t. Are you with me? So, f is the name of the function, or g or k, whatever they put there. And this right here, this variable in the parentheses, this tells me the variable I'm going to find on the other side of the equal to sign. Good? Okay, let's look at another one. Here's an equation, and they're asking us if this equation actually represents a function or not. Remember, for every input, that's right, you have one output. So, plug in a number. Plug in 0. What would I get? I'd get a single answer. I'd get 8/3. Plug in 1. What would you get? Yeah, you'd get 8/4, which is 2, but you get a single answer, don't you? Okay, we'll plug in -1. What would you get? Yeah, you get 8/2, which is 4, but the point is you get a single answer, don't you? Now be careful, because I already hear some of you. Some of you are going, yeah, but you can't plug in. That wasn't their question. Their question was not what I can't plug in. Their question was, when you plug in a number, do you only get a single answer for y? And I do. I get a single answer for y. Even if I plugged in that -3, I would still get a single answer, and that answer would be undefined. Are you with me? Every time I plug in a number, I get a single answer. So yes, this definitely represents a function. Cool? Okay. Let's look at another one. And let's see. Some of you are like, what's this funky little symbol right here? Well, let me rewrite it. This is y equals plus or minus the square root of 9 minus x squared. With me? That says plus or minus. So now, when I plug a number in for x, the question is, how many answers am I going to get out? Right? So, let me just create a table. If I plug in 0 for x, that means you would have plus or minus the square root of 9, wouldn't you? Because the x being 0, 9 minus 0 would just be 9, wouldn't it? Okay, well, what's the square root of 9? Yeah, according to what we already know, the square root of 9 is 3. So when I plug in 0, I would get 3. But this symbol tells me you don't just get a positive 3 as an answer, you also get a -3. So this single input of 0 gave me 2 outputs. So is this going to represent a function? Now, This one is not a function. That plus and minus told me right away you're not getting a function. Cool? Okay, one more. Let's look at this one. Now, do you notice on this one my y is squared? But do you notice on previous problems that we've done, the y has been by itself? There hasn't been anything with the y. It was just y equals, y equals, y equals. This is y squared. So that means that, yep, you got to get y by itself. And how do I get rid of a square? Good, you're going to square root both sides, aren't you? Which means you're going to get y equals the square root of 3 minus x squared. Agreed? Okay, not quite. Some of you are like, why not? Well, here's why not. Do you know what this little square on the y tells me? That tells me 2 answers. Which means when you take the square root, you don't just get a positive answer, you also get a negative answer. This tells me I'm supposed to get 2 answers for y. Just like in the past, when you have solved second-degree equations, and you're like, well, how many answers are you going to get? This square tells you you're getting 2 answers, doesn't it? Well, just because the square is on the y doesn't mean that the meaning changes. I'm still going to get 2 answers for y. So question, is this a function? Nope, definitely not a function. Cool? Okay, hopefully this makes some sense to you. Hopefully you're understanding this lecture. You keep going, and I'll catch you on the flip side.
Okay, so now let's talk about finding the domain of a function. You know, it's easy to find the domain of a graph because all you're doing is you're looking at the x-axis of a graph and deciding what x values the graph is using. But sometimes when it comes to an actual function, an actual equation, so to speak, for example, sometimes it's not so easy to determine the domain of an actual function. So here's the deal. In order to find the domain of a function, you need to remember 2 red flags. These 2 red flags are going to help you find the domain of actual functions. So one red flag is a denominator. And you're like, why is that a red flag? What do I have to worry about? Well, let me ask you something. What's the one thing a denominator is never allowed to be? What's the one number a denominator is never allowed to be? Yeah, that's right. Your denominator is never allowed to be equal to 0. That's why it's a red flag. The second red flag is an even root. A square root, a fourth root, a sixth root, all those roots. And you're like, well, what's the deal with those? Why would that be considered a red flag? Well, can you take a square root of any number you want? Go ahead, think about it. Sure, you can take the square root of 4. Sure, 9. Even 7, you're right. Can you take the square root of 0? Sure, 0. But what about taking the square root of negative 4? Ah, yes. We can't take the square root of negative 4 because we have to leave our real number system and go into this imaginary number system in order to find that square root of a negative number. So here's the deal. And why are even roots a red flag? Because if I want to stay in my real number system, I'm only allowed to take the square roots, fourth roots, sixth roots of even numbers, of positive numbers. I'm only allowed to take square root, fourth root, sixth roots of positive numbers. Are you with me? And how do you know when a number is positive? Some of you said it, because it's greater than 0. But here's the deal. 0 is the joker in the deck. 0 is also considered a positive number when I need it to be. Cool? All right, so let's take a look at this first example here. I want to find the domain of this particular function. Now here's something you need to understand. There's actually an initial domain going on that you may not have realized. And the initial domain is every real number in the world, from negative infinity to positive infinity. Got it? And you're like, all right, so, well, here's your goal. Your goal is to try and kick out a number from that initial domain. And I'm just going to short it for ID. Your goal is to try to kick out a number from the initial domain. That's your goal. Sometimes you can and sometimes you cannot. And how are you going to kick out a number if there's a number to kick out? You are going to look at red flags. You are going to ask yourself, do I have a red flag? Well, gratefully there's only 2 of them. So let's find out. First red flag is a denominator. Do I have any denominators in this function? No. So no one's getting kicked out of this initial domain. Second red flag is an even root. Do you have an even root here? No, you don't. So you're not kicking any numbers out of this initial domain. So did I have any red flags? Nope. Am I kicking any numbers out? Nope. So you know what? In this case, the final domain is exactly the same as the initial domain. Negative infinity to positive infinity. You didn't kick anybody out. Are you with me? Okay, let's do another problem. I'm going to get myself a little bit of board space here. All right, because I think I might need it. Hopefully you wrote down the red flags because we're going to need it in this next problem. These red flags are your friends. Trust me. These red flags are your friends. Whenever they say find the domain of a function, they didn't give you a graph, they didn't give you a mapping, they didn't give you any data points, then you need to think those red flags. So, problem number 2. I have f of x equaling 2x squared minus 3x plus 1. And I'm trying to find the domain of this particular function. With me? Okay, so just like before, I need to remember there's always an initial domain. And my initial domain is negative infinity to positive infinity. Are you with me? Cool. And what's my goal? Yeah, my goal is to see if I'm going to kick any number out of that initial domain. This goal remains the same, regardless of what it gives me. After I realize my initial domain, my goal is to see if I'm going to kick anybody out of this initial domain. And how do we do it? We do it by asking ourselves, do we have any red flags? That's the question. Are there any red flags? Remember one of the red flags. One of the red flags is, yeah, a denominator. Do I have a denominator in here? Nope. So am I kicking anybody out of this initial domain? Nope. What's the second red flag? Yeah, an even root. A square root, a fourth root, a sixth root. Do you have that here? Now, some of you may be saying yes, and some of you may be saying no. So here's the deal. Here's what I need all of you to do. I need all of you to air draw me a square root. Go ahead, I'll wait. Air draw a square root. Did you do it? Okay, I don't know about you, but when I air draw a square root, it's going to look like that. Do you see this square root here? No. So is a square root, if that square root's not here, do I have that red flag? Nope. So I don't have any red flags in this case, do I? Nope. So am I kicking anybody out? Nope. So my final domain then, in this case, is the same as the initial domain, from negative infinity to positive infinity. Cool? Okay, so hang in there. I've got a few more examples. Here are a couple more examples about finding the domain. Let's look at number 3. So remember, to find the domain, we first need to realize we have an initial domain. And I'm going to abbreviate initial domain with ID. And your initial domain, that's right, is every real number in the world. Okay? That's all at your disposal. And what's your goal? Your goal is to see if you're going to kick anybody out of this initial domain. That's your goal. Always remember there's a goal here. Okay? Always remember the goal. Are you going to kick any numbers out? And I'm going to write the word goal because I need you to remember that you have one. Now, the only way you're going to kick any numbers out of the initial domain is if you have a red flag. So, let's look. Do I have a red flag? What's one of my red flags? Denominators. Good. Do I have a denominator here? I certainly do. So yes, we have a denominator in this case. We have a red flag. So what's the deal about the denominators? Why are they a red flag? Why do they say danger, Will Robinson? Yeah, you're going to have to go look Lost in Space up for that one. Anyway, yeah, your denominators can't be equal to 0. So what is my current denominator? Good. X plus 3. And what did you just tell me about the denominators? That's right. Your denominator is not allowed to be equal to 0. So x plus 3 can't be equal to 0. So when I solve, I end up with x not being allowed to be a negative 3 in this case. So you found a number to kick out, didn't you? Out of the initial domain, I can use any number I want except for that negative 3. So some of you are like, well, how do I write that? There's two ways of writing it. One way is set notation. Set notation says the set, that's how those braces are read, the set. And what variable am I talking about? X, such that. That's what that line means. That straight line, that vertical line means such that. The set of x such that. What did you just tell me? That's right. X cannot equal negative 3. Cool? Okay. There is another notation that we can use, and that's interval notation. So let me refresh your brain on interval notation. The interval notation comes from a graph. So if I look at x not being allowed to be a negative 3, if I look at my number line, negative infinity, positive infinity, and at negative 3 we're going to put an open circle. And we can shade everything on this side of the negative 3 and everything on this side of the negative 3. I just can't shade the negative 3 because it says x can't be negative 3. Good? So when it comes to the interval notation, the shading says I can start at negative infinity and I can go up until negative 3. And since a negative 3 has an open circle, that's right, you put a parenthesis. And the shading picks up at negative 3, believe it or not, and goes all the way to positive infinity. And still a parenthesis on that negative 3 because there's an open circle. And how do you keep these two interval notations together? Because it's supposed to be one sentence, one answer. Yeah, you put it with a union. So depending upon the directions, you may need to write the answer in set notation or you may need to write interval notation. And interval notation comes straight from a graph, so always remember that. Good? Okay, let's look at number 4. Directions haven't changed. They would like me to find the domain. And yes, we have the initial domain that we need to remember. And the initial domain is anywhere from negative infinity to positive infinity. And what are you trying to do? Yeah, your goal is to kick a number out of here, right? Always remember there's a goal here. So I'm going to write it in the same color. Why? Because I want you to remember that along with the initial domain, you always have a goal. And the only way to try and kick a number out is if you have a red flag. So, do I have a red flag? Yeah, I have a denominator in this case. By the way, I forgot to check over on number 3. Do I have a square root? No. Just because you have one red flag doesn't mean you wouldn't have both of them. So just FYI. So do I have the square root here also? No. Very good. That square is not a square root, right? Okay. So my denominator is x squared plus 3x minus 10. And that denominator, that's right, is not allowed to be equal to 0. So now we get to solve this. And yeah, this little square here tells me to factor. So yes, I am expecting that you remember how to factor a second degree equation that is this simple. Okay? And if you're like, okay, that wasn't simple, go back and look at some factoring videos. All right? You'll find out that this one is actually Not too bad to factor. All right, and I take each one of these and I set them not equal to 0. Agreed? Which means in this case, x cannot be equal to a negative 5, and x cannot be equal to a positive 2 when you set each one. Agreed? Okay, so 2 ways to write it. You have set notation, and set notation says the set of x such that x cannot equal negative 5 or 2. Good? And then you've got the interval notation. And the interval notation comes from a graph. So I'm going to get myself just a little bit of board space here so we can work and we can see what's going on. All right? So this graph is going to go from negative infinity to positive infinity, isn't it? It certainly is. And the two numbers that you care about on this graph are, good, a negative 5 and a positive 2. So we have negative 5, we have positive 2, and those are both open circles because x cannot equal those, right? X cannot equal those. But x can be all of these numbers and all the numbers in between and all the numbers out here, can't they? So I'm going to write my interval notation up here underneath the graph so it's a little bit easier to see. So according to this graph, the interval notation answer is going to look like negative infinity to, good, negative 5, right? Because that's where the shading ended with a parenthesis because there was an open circle there. But then the shading picks up at negative 5 and it ends at 2 because there's another open circle, right? And then again it picks up at 2 and goes to infinity. And yes, we have to put the union in between because that keeps these three things all together in one sentence. So my x's are in this interval or, remember the union means or. My answers, my x's are in this first interval or this second interval or that third interval. Those would be the x's I would be allowed to use for that particular function. Good? Hang in there. Okay, so I'm back. So let's look at number 5. We're still asked to find the domain. And so remember the initial domain is, that's right, negative infinity to positive infinity. And you have a goal. What's your goal? Your goal is to try to kick any numbers out of that initial domain, right? But the only way you can kick any numbers out is if you have a red flag. So let's take a look. Do I have a red flag? One of my red flags is a denominator. Does this function have a denominator? Nope. What's your other red flag? That's right, an even root, like a square root, a fourth root, a sixth root. Do we have a square root? Yeah, we sure do. We've got that square root here, don't we? By the way, most authors of the book drop that little 2. That little 2, that index, means square. This symbol means root. So that little index means square, and the symbol itself means root. So this is a square root. So what was the deal about a square root again? What was the deal about the number under the square root? It always had to be what kind of number? Yeah, positive. Because if I try to take the square root of a negative number, I end up in the imaginary world. I don't want to be there. I want to stay in my real world because my real world is from negative infinity to positive infinity. Got it? That's why we don't want an imaginary number. That's why we need to make sure this thing is positive. And again, how do I know when I have a positive number? Yeah, don't tell me because there's no negative sign in front of it. That ain't it. How do you know when you have a positive number? We said it at the beginning. Yeah, when it's greater than or equal to 0. Cool? All right, let's do some solving. So move the 3 onto the other side. Divide by a negative, and when you divide by a negative, what happens to the inequality sign? Yep, it flips on you. Isn't that just lovely? Make sense? Now I know some of you are going, why does it flip? Hang in there. I'll get to that in a moment. All right? Okay. So we have two ways of writing the answer. One is the set notation, and set notation says that it's the set of x such that, that's right, x is less than or equal to 3/2. And the other notation is, good, interval notation. Now, interval notation always comes from a graph. Well, if I take a look at the graph for this one, at 3/2, we have a solid circle, right? And x is supposed to be less than that, which means that's everything to the left of the 3/2. And that's negative infinity out there, isn't it? So, good. Negative infinity to positive 3/2 with a bracket. Because of that solid dot, because of that equal to sign. Cool? Okay. Take a look at number 6. All right, what's the, that's right. We have an initial domain of negative infinity to positive infinity, and our goal is, that's right, to kick numbers out of the real number system, the negative infinity to positive infinity. And the only way to do that is with a, good, red flag. So, the question is, do I have a red flag? As a matter of fact, I got both of them. I have a denominator, and I've got the square root, don't I? I've got both red flags here, don't I? Okay, so now hang in there a second. This 3x plus 4, the square root says it has to be positive, right? And positive numbers are, good, greater than or equal to 0. But it's also a denominator. And what's the denominator say? Yeah, the denominator can't be equal to 0, which means, watch closely, I get rid of the equal to sign under this inequality. So in other words, this 3x plus 4 can only be greater than 0. It cannot be equal to 0 because of the denominator. Are you with me? Again, it can be greater than 0 because it has to stay positive for the square root, but it can't be equal to 0 because it was in the denominator. Yeah, got a twofer here. Okay, so let's go solving. So 3x is greater than negative 4, and x is greater than negative 4/3, right? Okay, set notation. Yeah, set notation is going to say the set of x such that x is greater than negative 4/3. Good. The interval notation. Again, let's get a graph here. And here's the negative 4/3 with an open circle because it's not equal to, and everything to the right of it because I'm looking for numbers that are greater than it. So, interval notation says that our shading will start at negative 4/3, but it's a parenthesis, not a bracket because it's not equal to. And it goes all the way out to infinity with a parenthesis. Cool? Okay, now some of you are going, yeah, but okay, back up. What about this flipping again? Why do we flip the inequality sign again when we're dealing with dividing by a negative? All right. Do you agree that 2 is less than 3? So do I. If I multiply both sides by a negative 1, I'm going to keep life easy for us. Then I have a negative 2 on this side and a negative 3 on this side, right? Good. Which number is larger? Yeah, the negative 2. Inequality sign flipped. Whenever you multiply or divide by a negative number, what used to be the smaller number now becomes larger. What used to be the larger number now becomes smaller. That's why you flip the inequality signs when you multiply or divide by a negative number. Cool? Hang in there. Got something else for you. Okay, so let's talk about our fancy substitution notation. All right? Remember what f of x means. F is just the name of this new equation, okay, or this new function. This f could have been g. It could have been h. It could have been g of x, h of x, t of x, whatever we wanted it to be. But we usually use f because f stands for function. Good. So if over here I wanted to find f of 2, notice the x was replaced by the 2, wasn't it? Which basically tells you that x now equals 2. Which means over here on this side of the equal to sign, instead of saying 2 times x, you would say, good, 2 times 2 plus 1, which would give you 5. So f of 2 would equal, good, 5. Now, by the way, you could write that as a point because what was your input? Your input was 2. What was your output? Your output was 5. So you could actually write that as a point. Just saying, in case they say something about it. Cool? Okay. What happens if they said f of k? So now what does x equal? Good. X is now equal to k. So instead of saying 2 times x, you would say 2 times k plus 1. And that would be about all you could do with that. And you're like, can you still write a point? Actually, you can still write a point. Your point would look like the input, which was, good, k, and then the output, which was, yep, 2k plus 1. That one looks a little funny, but that's what you would write if they wanted you to write a point. Cool? All right. Now we're going to talk about this difference quotient. Now this difference quotient you will use more in calculus, so I'm just letting you know that. But for now I need to make certain that you understand it, because here's the deal. This is still using a substitution notation. All right? They want you to find f of x plus h. And we're going to go ahead and use this function over here, the 2x plus 1. So here's the deal. First things first, you need to find f of x plus h, which means instead of x, I now have x plus h. So instead of saying 2 times x, you will now say 2 times, that's right, x plus h. Plus the 1 still at the end, right? Okay, which means this is equal to 2x plus 2h plus 1, isn't it? Good. Now, they also have f of x here, don't they? Okay, so f of x is simply 2x plus 1, isn't it? Good. Now, let's put the difference quotient together. Now that we found like this first part, and now that we have the second part, so here's your first part and here's your second part, let's put it together. So the first part is f of x plus h. I'm supposed to write that. Well, what did we get? We got 2x plus 2h plus 1, didn't we? And then we're supposed to subtract the second part, which was simply 2x plus 1. And this whole thing will be divided by h. With me? Okay, so I don't like the parentheses being here, so let's get rid of them. This would just simply be 2x plus 2h plus 1, right? In front of the second parentheses, that minus sign, so that 2x will be, good, minus 2x, and yes, minus 1. Agreed? All over h. Okay, you see what's going to happen? I'm noticing a positive 2x and a minus 2x. I'm noticing a positive 1 and a minus 1, which is leaving me 2h divided by h, which is just 2. Cool? Okay, so we have talked about functions, domain, even the definition of a range. We've talked about finding if something is a function by a graph or a mapping, and then we actually talked about that finding the domain from actual functions, as well as this wonderful substitution stuff. So we've spoken about quite a bit today. Anyway, you have fun with this stuff, and I'll catch you on the flip side.